7 days ago, something changed. Astronomers monitoring 3I Atlas noticed readings that shouldn't exist, data that violated predictions, behavior that broke the rules we've relied on for understanding Comet. Not subtle variations, not measurement uncertainties, clear, unmistakable deviations from physics that's worked flawlessly for every other comet we've studied. Multiple independent observatories confirmed it, NASA verified the measurements, and now we're watching an interstellar visitor demonstrate that our models, comprehensive as they seem, don't describe reality when objects from other stellar systems enter the picture. This isn't the first time 3I Atlas has surprised us. It's been breaking expectations since discovery. But what happened in the last week crosses new thresholds. Massive material loss occurring suddenly. Non-gravitational acceleration exceeding anything outgassing alone should produce. Brightness and color changes that don't match standard cometary physics. Ground-based telescopes in Chile and Hawaii captured it. James Webb Space Telescope measured the chemistry. Hubble imaged the structural changes. Independent facilities across 3 continents reached the same conclusions. This is real. This is confirmed. And this is forcing scientists to acknowledge that interstellar comets operate under rules we're only beginning to understand. The timing matters. 3I Atlas just emerged from solar conjunction. For weeks, it was too close to the sun's glare for observation. Telescopes couldn't track it. During that observational gap, something happened. And when visibility returned, the comet had transformed. New jets appeared. The coma expanded dramatically. Spectroscopic signatures shifted, and the trajectory showed acceleration that standard models can't explain through thermal effects or normal volatile sublimation. Something else is operating, something we haven't accounted for. This is the story of what happened, what the data shows, why it matters, and what scientists expect might occur next, as 3I Atlas continues surprising us with behavior that textbooks say is impossible. Understanding what makes the last 7 days extraordinary requires understanding what changed, what measurements deviated from predictions, what observations forced scientists to revise their assessment of 3I Atlas. First observation, massive material loss. Spectroscopy before solar conjunction showed steady but moderate outgassing. Carbon dioxide dominant, water present, ratios consistent with previous measurements. Activity levels matching predictions given the comet's distance and solar radiation intensity. Post-conjunction spectroscopy tells a different story. Material release rates increased by factors, not gradually, suddenly, as if internal reservoirs that were sealed suddenly vented. Hydroxyl emission indicating water sublimation spiked to levels far exceeding thermal model predictions. Carbon dioxide production surged beyond anything observed previously. The scale is unprecedented for an object this far from the Sun. At current distances, 3I Atlas should be cooling. Activity should decline as solar heating weakens. Instead, outgassing intensified. Material pours into space at rates that require energy sources beyond what solar radiation provides at these distances. Second observation, non-gravitational acceleration. Precise astrometry before conjunction established. 3I Atlas trajectory with high confidence. The orbit was known. Future positions were predictable. Standard gravitational calculations accounted for solar gravity, planetary perturbations, everything that should affect the path. Post-conjunction astrometry reveals deviation. The comet isn't where pure gravitational predictions said it should be. The discrepancy indicates acceleration beyond what gravity alone produces. This happens with comets. Asymmetric outgassing creates rocket effects. Gas escaping preferentially from one side pushes the nucleus. But the magnitude of 3I Atlas acceleration exceeds what normal outgassing should produce. The observed position offset requires momentum transfer greater than typical cometary jets provide. Either the outgassing is extraordinarily asymmetric, concentrated in narrow jets with unusual geometry, or additional forces are operating. Third observation, color and brightness transformation. Before conjunction, 3I Atlas appeared relatively neutral in color. Spectral analysis showed emissions consistent with dusty coma containing typical silicates and carbonaceous materials mixed with gas. Post-conjunction observations show dramatic bluing. The coma appears significantly bluer than before. Blue coloration in comets indicates specific chemistry. Ionized carbon monoxide produces strong blue emission. Certain carbon radicals contribute blue signatures. Finding intense blue suggests chemical changes. Either new compounds are being released or ionization processes intensified dramatically. Brightness also changed unexpectedly. Not just from increased activity, the comet appears brighter than models predicted, given its distance and estimated size. Either the nucleus is larger than initial assessments suggested, or reflectivity changed, or dust properties altered, or multiple factors combined to produce unexpected brightness. These aren't isolated anomalies. They're related. Massive outgassing drives non-gravitational acceleration. Chemical changes produce color shifts. Increased dust production affects brightness. The observations form a coherent picture of a comet undergoing transformation that standard physics doesn't predict should occur at these solar distances. Comment below. What do you think is causing 3I Atlas to behave so unusually? The reason these observations are problematic is they violate principles that work reliably for solar system comets. Thermal physics that predicts activity based on solar distance, outgassing models that connect sublimation rates to nucleus properties, dynamics that relate non-gravitational forces to measurable gas production. For typical comets, these frameworks succeed. Predictions match observations within acceptable margins. Brightness curves follow expected patterns. Trajectories show non-gravitational effects consistent with observed outgassing. Colors correlate with known chemistry. The models work. Then 3I Atlas enters the picture and the models fail. Activity doesn't follow thermal predictions. Non-gravitational acceleration exceeds what observed outgassing should produce. Colors indicate chemistry that shouldn't dominate under these conditions. The energy budget is particularly problematic. At 3I Atlas current distance, solar radiation intensity is approximately 9% of Earth flux. This provides the energy available to heat the surface and drive sublimation. Standard thermal models use this input to calculate how much ice can sublimate per second. The calculated rates don't match observations. The measured material loss exceeds what solar heating alone should produce by substantial factors. Either 3I Atlas has properties that make it extraordinarily efficient at converting solar radiation to sublimation energy, or internal energy sources supplement solar heating. Candidate internal sources include radioactive decay. Long-lived isotopes like potassium-40 or uranium-238 generate heat through decay. If 3I Atlas contains unusually high concentrations of these isotopes, internal heating could drive activity beyond what solar radiation alone provides, but this requires explaining why an interstellar comet would have isotope abundances dramatically different from solar system objects. Different stellar nucleosynthesis, formation around a star with unusual metallicity, enrichment processes during formation that don't occur in our protoplanetary disk. Alternative explanations invoke exotic chemistry. Perhaps the unknown compound James Webb, detected at 4.5 micrometers, undergoes exothermic reactions. Chemical processes that release heat when molecules transition between states or react with each other. This heat supplements solar input and drives enhanced sublimation. Testing this requires identifying the unknown compound, determining its chemical properties, modeling whether proposed reactions generate sufficient energy. None of this is simple. The compound remains unidentified despite extensive spectroscopic analysis. The non-gravitational acceleration problem has similar issues. Typical cometary acceleration comes from asymmetric outgassing. If jets emit preferentially from one hemisphere, the escaping gas carries momentum. Conservation of momentum requires the nucleus recoils. This produces measurable acceleration. For 3I Atlas, calculating the required outgassing asymmetry to produce observed acceleration suggests extreme jet concentration. Nearly all the gas would need to escape from a small fraction of the surface, all oriented in specific directions. While possible, this seems unlikely given that spectroscopy shows distributed emission from the coma rather than concentrated from point sources. Alternative explanations propose that 3I Atlas experienced an impulsive event during conjunction. Perhaps internal pressure buildup released suddenly. Perhaps a large fracture opened. Perhaps the nucleus partially fragmented. Any of these could produce sudden acceleration beyond what steady outgassing generates. But without continuous observation during conjunction, confirming these scenarios is difficult. The event, if it occurred, happened when the comet was unobservable. We see the results but didn't witness the cause. When NASA confirms anomalous observations, it carries weight. NASA's Jet Propulsion Laboratory handles trajectory calculations for near-Earth objects, including interstellar visitors. Their orbital solutions incorporate data from observatories worldwide. When JPL says 3I Atlas trajectory shows non-gravitational effects, that conclusion is based on comprehensive analysis. Multiple observation campaigns contributed data. Ground-based astrometry from facilities with precise position measurement capabilities. Space-based observations from Hubble, providing high-resolution imaging. Radio telescope ranging if available. Every data set contributes to refining the orbit. The analysis accounts for all known forces. Solar gravity, calculated using current solar mass estimates. Planetary perturbations from every major body in the solar system. Relativistic corrections from general relativity. Even solar radiation pressure acting on the nucleus and coma. After accounting for everything predictable, residuals remain. The observed positions don't match predicted positions. The discrepancy has consistent direction and magnitude, suggesting systematic acceleration rather than random noise. This is the non-gravitational component. Quantifying its magnitude requires complex modeling. How much momentum is the comet gaining per unit time? What outgassing asymmetry would produce this? Are there alternative explanations? NASA's confirmation means these analyses have been performed and the conclusions are robust. Similarly, spectroscopic confirmations from James Webb carry authority. Webb's instruments are calibrated to extraordinary precision. When Webb reports specific molecular emission line strengths, those measurements are reliable. If Webb says carbon dioxide emission increased by certain factors, or that blue-emitting species intensified, those findings represent actual changes in the comet's chemistry. Ground-based telescope confirmations add confidence. When independent facilities in Chile, Hawaii, and Canary Islands all measure similar brightness changes, when multiple spectrographs detect the same emission line variations, when different imaging systems show consistent morphological evolution, the observations become bulletproof. This is why NASA confirmation matters. It means the anomalies are real, not instrumental artifacts, not analysis errors, real physical phenomena that require explanation. And if standard physics doesn't provide that explanation, then understanding requires expanding frameworks to accommodate new processes or conditions. Subscribe now, because what happens next could reveal whether 3I Atlas anomalies are unique to this object or representative of interstellar comet behavior generally. The critical unknown is what occurred during the weeks. 3. I Atlas was unobservable. Solar conjunction means the comet was angularly close to the sun from Earth's perspective. Observing it required pointing telescopes near the sun's position. Scattered sunlight overwhelms faint objects. Observations become impossible. This created an observational gap. Last measurements before conjunction showed 3I Atlas in one state. First measurements after conjunction revealed it transformed, but the transformation itself went unwitnessed. Scientists must infer what happened from comparing before and after states. Several scenarios seem possible. Perhaps 3I Atlas passed through perihelion, closest approach to the sun, during conjunction. If perihelion occurred when observations were impossible, the comet experienced peak solar heating without monitoring. Perhaps this heating triggered the changes now observed. Checking orbital calculations confirms perihelion timing. Yes, closest solar approach occurred during the conjunction gap. 3I Atlas reached minimum distance from the sun when it was effectively unobservable from Earth. This timing is unfortunate scientifically, but explanatory. Perihelion represents maximum stress on cometary nuclei. Solar heating peaks. Thermal gradients reach extremes. If the nucleus contains structural weaknesses, perihelion is when they're likeliest to fail. Fractures could propagate. Internal pressure could vent explosively. The nucleus could even fragment partially. Any of these events would produce the observations now documented. Massive material loss from sudden venting, non-gravitational acceleration from impulsive gas release, chemical changes from exposing fresh interior surfaces that have different composition than the weathered exterior. This scenario is plausible. It fits the timeline. It explains multiple anomalies simultaneously through a single perihelion stress event. But it remains speculation because nobody observed perihelion directly. The comet was behind the sun doing whatever it did without witnesses. Alternative scenarios propose that 3I Atlas properties make it respond to perihelion differently than typical comets. Perhaps its exotic chemistry produces delayed responses. Solar heating during perihelion-activated processes that manifested days or weeks later after the comet emerged from conjunction. Or perhaps the unusual carbon dioxide dominance means 3I Atlas responds more vigorously to perihelion than water-rich comets would. Carbon dioxide sublimation accelerates rapidly with temperature. If internal carbon dioxide reservoirs reach critical temperatures during perihelion, subsequent venting could be dramatic and sustained. Testing these scenarios requires modeling that incorporates 3I Atlas specific properties, not generic cometary models, but simulations accounting for 8:1 carbon dioxide to water ratios, possible exotic compounds, whatever internal structure the nucleus actually has. Such modeling is ongoing. Research groups worldwide are developing simulations attempting to reproduce observations. Which combination of nucleus properties, composition, structure, and perihelion heating produces the measured outcomes? The answers will constrain what 3I Atlas actually is. Given what's been observed, what should we expect in coming days and weeks? Will 3I Atlas continue surprising us? Will it return to more predictable behavior? Will entirely new anomalies emerge? Predictions are difficult because 3I Atlas has consistently exceeded expectations. Every time scientists think they understand its behavior, new data forces revision. But based on current observations and ongoing modeling, several scenarios seem plausible. First possibility, continued enhanced activity. If perihelion triggered processes that remain ongoing, material loss might stay elevated. The coma could remain bright and blue. Non-gravitational acceleration might persist as asymmetric outgassing continues. 3. I-Atlas would maintain its anomalous status for weeks or months. This would provide extended observation opportunities. More spectroscopy to characterize the chemistry. More imaging to document morphological evolution. More astrometry to refine non-gravitational acceleration measurements. The longer unusual behavior persists, the more data accumulates, the better we understand what's happening. Second possibility, fragmentation. If perihelion stresses weaken the nucleus, delayed fragmentation could occur. The nucleus might split into multiple components. Each fragment would develop its own coma. Tracking fragment separation reveals pre-split rotation and helps characterize internal structure. Fragmentation would be spectacular scientifically. Fresh interior material would be exposed. Spectroscopy of different fragments might reveal compositional gradients. If the nucleus is layered, different layers would appear as distinct fragments with different properties. Ground-based telescopes are monitoring for signs of splitting, any change in the coma's apparent size or shape, any emergence of multiple condensations suggesting separate nuclei. If fragmentation occurs, rapid response imaging with Hubble could resolve individual fragments. Third possibility, return to quiescence. Perhaps the perihelion triggered events were transient. Perhaps whatever drove the enhanced activity is depleting. Perhaps 3I Atlas will fade back toward predictions as it moves farther from the sun and conditions become less extreme. This would be anticlimactic but still informative. It would indicate that the anomalies were perihelion specific rather than inherent to 3I Atlas throughout its journey. The comparison between pre-perihelion behavior, perihelion response, and post-perihelion evolution would constrain what physical processes operated. Fourth possibility, entirely new surprises. 3. I-Atlas has consistently done the unexpected. Perhaps phenomena we haven't even considered will emerge. Perhaps the chemistry will reveal more unknown compounds. Perhaps structural changes will produce observable effects. Perhaps interactions with solar wind will create unusual tail dynamics. Scientists are maintaining observing programs precisely because predictions are uncertain. Continuous monitoring ensures that transient events get captured. Whatever 3I Atlas does next, telescopes will be watching. 3. I-Atlas behavior matters beyond just one unusual comet. It informs our understanding of interstellar objects generally. It reveals what diversity exists among visitors from other stellar systems. It tests whether frameworks built on solar system experience apply universally. We now have 3 confirmed interstellar visitors. 1, Oumuamua, showed no activity and mysterious acceleration. 2, Borisov, displayed conventional cometary behavior. 3, I-Atlas demonstrates extreme anomalies, including impossible acceleration and exotic chemistry. 3 objects, 3 completely different profiles. The statistical sample is tiny, but the diversity is evident. Interstellar objects don't follow simple patterns. They don't all resemble solar system comets. Each visitor from beyond brings new surprises. This diversity challenges planning for future encounters. If we can't predict how interstellar visitors will behave, designing observation strategies becomes difficult. What instruments are needed? What measurements are priorities? What should rapid response protocols include? 3. I-Atlas suggests that comprehensive characterization requires capabilities across all wavelengths and all techniques. Spectroscopy from ultraviolet through infrared, high-resolution imaging, polarimetry, astrometry, everything simultaneously because we don't know in advance which measurements will prove critical. It also emphasizes the value of continuous monitoring. The conjunction gap during perihelion meant missing crucial events. If 3I Atlas had been observable throughout, we would understand much better what happened. Future missions might include spacecraft stationed at locations that maintain visibility when Earth-based observations are impossible. The acceleration measurements have implications for interstellar object detection. If comets can undergo sudden acceleration, their trajectories become less predictable. Objects might deviate from pure gravitational paths in ways that affect where they appear in the sky. Detection strategies might need to account for these uncertainties. From astrobiology perspective, 3 IATLALACE, continued demonstration of exotic chemistry, strengthens arguments for chemical diversity throughout the galaxy. If interstellar visitors routinely carry compounds we don't find in solar system objects, then prebiotic chemistry might be more varied than terrestrial experience suggests. This could affect how we search for biosignatures on exoplanets. If we assume Earth-like chemistry is universal, we might miss life based on different chemical foundations. 3. I-Atlas reminds us that chemistry varies, that formation conditions affect what molecules exist, that diversity is the norm rather than exception. As this recording ends, 3 I-Atlas continues outward, still releasing material at impossible rates, still showing non-gravitational acceleration that models struggle to explain, still appearing bluer than chemistry at these temperatures should allow. Telescopes tracked every change. Spectrographs capture every emission line. Cameras document every morphological evolution. Because this interstellar visitor is teaching us that the universe contains surprises, that objects from other stellar systems don't follow rules written based on local experience. That nature is more creative, more diverse, more unexpected than our theories accommodate. NASA's confirmation means these observations are real. Multiple independent facilities reaching the same conclusions. The data is solid. The anomalies are genuine. And the explanations require physics we're only beginning to develop. What happened 7 days ago when 3 I-Atlas emerged from conjunction represents another chapter in the ongoing revolution in understanding interstellar visitors. Each observation adds knowledge. Each anomaly refines our questions. Each measurement brings us closer to understanding how comets from other stars differ from those that formed here. The impossible has happened again. 3 I-Atlas accelerated when it shouldn't, released material at rates thermophysics can't explain, changed color through chemistry that remains mysterious, demonstrated that interstellar visitors are more than just distant relatives of solar system comets. They're fundamentally different objects formed under different conditions and behaving according to rules we're still learning. 7 days ago marked a turning point. When post-conjunction observations revealed transformation nobody predicted, when NASA confirmed measurements that challenged standard models, when 3 I-Atlas proved once again that interstellar visitors refuse to be conventional. And now we watch, monitoring for what comes next, whether continued activity or fragmentation, or return to quiescence, or entirely new surprises. Because 3 I-Atlas has taught us that predictions are dangerous when dealing with objects from beyond, that the universe doesn't follow our expectations, that nature will do what physics allows, regardless of what our models say is possible. The visitor from another star continues surprising us. The data continues accumulating. The mysteries continue deepening. And somewhere in these observations, in these impossible accelerations and unexplained chemistry and dramatic transformations, the truth about interstellar comets is revealing itself. One impossible observation at a time. Comment below. What would blow your mind the most: fragmentation, color change, or impossible acceleration? Subscribe now, because 3i Atlas story continues. Observations proceed daily. Analysis deepens weekly. And as this interstellar visitor keeps doing the impossible, we'll be here bringing you every update about what we're learning from this cosmic messenger that refuses to follow the rules. The comet that breaks physics is still breaking physics. The anomalies continue. The questions multiply. And the universe keeps teaching us that our comprehensive understanding of comets was never comprehensive at all. It was local, limited, built on narrow experience. And 3i Atlas is showing us exactly how much we still have to learn about the incredible diversity of objects traveling between the stars